welcome back Dr. Hanna for his second talk as part of this session.
Thank you so much again. The talk will switch from was clinical at the beginning. We're going to talk now more on the techniques. And this is the same disclosure that I have in the previous talk. So I presented this slide earlier just to highlight the fact this is really a genetic inherited disease. And I always try to explain that to my patient, thinking about our cells as really a textbook. And the way I explain how the mutation happened is with really a change in one of the letters. From an example here is the gray cat run down the hole. If we switch that letter, it truly changed the whole meaning. But it is really surprising what I want you to think about, how many other variables control the phenotype of the disease, because you would expect everyone to have the same phenotype, but unfortunately, many of patients have very severe, and some of them are very mild disease. And thanks to that astute observation by Dr. Francis Collins, who was the previous head of the NIH back in 1984, he published what it is that really was the initial paper about the persistence of fetal hemoglobin, that it described that can be a protective in terms of phenotype. So if a patient have very few F cells that express fetal hemoglobin, they have very severe phenotype. As they increase in their fetal hemoglobin, there is less sickling. And there is a magic number of 10 picogram per cell that seems to be protective of the cells. So even in a transplant, we always focus on that seem to be very helpful for the health of the red blood cells. And there is actually more ongoing now in terms of how do we measure the health of the red blood cells. And this disease and the idea of the gene therapy, it's really not novel. We are very excited we have it now, but thanks to many of the scientists, starting with Dr. Watson back in the 1950 when they described the DNA, and even earlier than 1921 when they described the sickle cell disease, has been multiple attempts to incorporate the idea that we can correct the gene. The most famous one was actually in the early 2000s to patients with severe combined immunodeficiency in the 1999, but unfortunately that patient developed leukemia, T-cell leukemia, and died. And that had set the field backward a lot because there was a lot of hesitancy after that. But with the advance in the technology, and truly, especially after CRISPR in the early 2000s, that has renovated the field to make it more precise. And that has led to the true approval really of 3 products. 2 of them is the same, Zynteglo and Lyfgenia, but they specifically for hemoglobinopathy will be helpful. I'm showing this slide because I want to emphasize that there is difference between cellular therapy and gene therapy. When it comes to sickle cell and thalassemia, it is a combination of cell and gene therapy because there is actually many other gene therapy products, they don't need the cell to be delivered. We can induce the changes without needing a cell as a mechanism or transporting for that. So trying to be careful with the terminology, and the ASBMT last year, they did have a consensus paper to try to be really careful in what we are calling a cellular therapy, genetic therapy, or others. And this is very helpful for me and for many of my colleagues to differentiate even with the cellular therapy, to think about it, not even with the CAR T that we think about it. There is more now going to come from allo CAR T. Not all of them going to be an auto, and the same thing potentially in the future from a gene therapy. And even within the cell itself, you are going to start to see more different type of cells. Not all of them going to be in the hematopoietic stem cell that are in the middle, what we call the multipotent stem cell. There may be some other cells coming, but the one that we are mostly familiar with them, it is the immune type of cells, the T cell, and some of now NK CAR T also are being developed. So let's switch now back to that delivery that I mentioned earlier. This is really important because many of our therapies now for sickle cell and thalassemia depend on the ex vivo. But our goal, hopefully in the future, to be able to do in vivo, because that would eliminate the need potentially for a chemotherapy or others. So the ex vivo, similar to what I showed you in the previous talk, we take the stem cell, we send them to the lab, that's outside the body, that's when there's the gene addition or the gene editing is gonna occur. The in vivo, it happens inside the cell. The patient will basically giving them the vector, and the vector will go to the cells. This is what happened with our hemophilia gene therapy products. They use adenovirus-like product that it will go directly to the liver, and they will use the liver cells to start to produce the product. No need for any ex vivo at that time. That's why many patients, when they come to me as a consult for sickle cell, they think it's just an injection, I'm gonna give it in the clinic and it's done. But that's when they get surprised how much long is the journey and how many complications they could be. So let's now start with each of the therapy of the gene modality of gene therapy and go over each one in details. The first is the gene addition, which is really the pioneer. This is what was for the last 20 years, starting with that SCID patient that I showed, then the ADA, adenosine immunodeficiency, that was also with the SCID, and later with the lentiviral product with Lovocell. This is basically a cell that has the hemoglobin gene mutated. What we will do usually, we will have a vector, and it could be different type of vector. In this case, of the Lyfgenia or Zynteglo, we will use a viral vector, and we're going to differentiate between the two different. That induce a functional DNA that's going to produce what it is missing from the cells in addition. So you will see that that's important for many patients because they think that, oh, I'm just going to take away the hemoglobin S. No, I am going to introduce an additional hemoglobin, and that balance in the hemoglobin is important. If you remember that two patients I mentioned, one with the having persistent anemia, that was due to an alpha thalassemia too. So if you have a very low in terms of alpha thalassemia, and that's why we need to do genotype for this, it's important to achieve a balance. If you don't have that balance, they will continue to have ineffective erythropoiesis. The vectors can truly be different. You could have a viral vector, or you could have synthetic vector. So the synthetic vector, we are becoming familiar with it with the messenger RNA, the COVID vaccine. Those are the things we are using nowadays. The technology is advanced that we can put a protein load or a DNA load or RNA load inside liposomes or even polymers versus the traditional old ways, which is the viral vector, and they can be divided either into integrating viruses or non-integrating viruses. And the decision point, how do you decide which vector do you use? It's going to depend on multiple factors. The one, it's how big is that DNA you are going to do. So that payload is an important variable and deciding which one to do. The transduction efficiency. The more you are using in the viral, there is really higher compared with some of the other methods. Long-term stable expression, because if it is not integrating virus, the more the cells divide, then the decrease in the expression. The target cell-specific tropism, some of the immunogenicity, because sometimes some people are actually, even with adeno-like virus, they can have some immunogenicity against it, and they will not have a good expression of that, and not have any genotoxic. So this is slide show the differences between the integrating viruses and non-integrating viral, and really this is depend on how much you want that product to continue and what it is your target cells. So the most common viral vector, it is the adenovirus-like or AAV or adenovirus-associated virus, and they tend to truly be less immunogenic. They will go to the cell, but the cell division, it will make it less. So that's why they target cells that it is not going to divide so much. So that's a problem for hemoglobin or anything, because the cells in our blood will dilute a lot. So you cannot use that method for that ability to express. And for the integrating vector, there is always a concern about where it will integrate. That's what it is used in the older ways with the gamma retroviruses that was used in the SCID patient, because the retroviruses, they will integrate, and that sometimes can be random. This is comparing the different viruses. I want to bring to your attention to that right column there, which show you really the benefit of the adenovirus and the AAV. They tend to be able to have a bigger payload in terms of DNA to help with the expression. Now we're going to switch. This is the same gene addition, but it is just having the same vector there. We're going to switch now to how do we insert that. So we talked about the viruses there, but the other now newer method, because we're trying to avoid any, how do I say it, anything that it is really not, we don't have enough confidence in some of these viruses sometimes on the long term. So there is a field is pushing toward trying to introduce any vector without having a viral integrated or non-integrated. And most of this research is going through the electroporation. But some of this concern with the electroporation, you need higher number of stem cell. You are losing more stem cell in this method compared to that. So there is balance between what you are going to benefit and what you are going to lose with that. The gene editing, they really depend on a mechanism in our body that it is important every day. When we have any damage in our cells, the body corrects itself, and it corrects either in the homology direct repair in the upper side or the non-homologous end joining. And this is important because this is depending on it, the following mechanism for how we correct. So whenever there is a correction or editing, and we're going to start with the CRISPR one, when we go and trying to edit the gene, there is going to be three things happening. Either we're going to just disrupt and make a cut in the DNA, and then the body will do either homologous or non-homologous repair. Then second mechanism is the gene deletion, where you can do two simultaneous cuts in the double strand. So you could cut it together and remove that gene. Or in the third mechanism for the gene editing, it is the correction or insertion. That it is must require to have homologous DNA repair, so the HDR. The other two will happen usually with the non-homologous end. And this is the gene disruption. It is what it is, the mechanism that it is used with the currently approved CRISPR-Cas9 or Cas9. So let's review how that is done. So this is the first generation of what I call the first generation of gene editing. It is really what it proved that concept. It uses the Cas9 and the CRISPR, and then with the guided RNA, they will be basically, the scissor will know where to make that cut. With that PAM, it will know where to be able to correct. But that it is not any correction. They just make an indel. They make a cut in the DNA. So you are going to target a gene, you wanted to turn it off. That's what will happen with the BCLA11. All we wanted, we want to make nonsense or missense mutation in that BCLA11. It will turn it off, and then the hemoglobin F will increase. So there is really no directed repair here. So that's the important one. Then, which is the study I mentioned and alluded to, and we will present that at ASH, about the base editing. The base editing, it is a single nucleotide change. It uses a variant from the Cas nuclease. It's called Cas9 nicase. It is a variant of that, but it also uses deaminase. That it is a different from the current method that it is used in the approved Cas9. This will usually modify the DNA base while the Cas9 is attached to it. So you will see and make a change directly in the base. So this is more precise method of how you will do the DNA. It will still use the guided RNA. What it is coming next, it is the prime editing. This is really even more, it can help you to make a repair beyond just one base. If you have a bigger changes in the DNA. So again, luckily the sickle cell, for example, it is one gene one nucleotide change, but there's many other diseases that it is more complicated changes. You're going to need a little bit longer. And then there are two methods. This is the zinc finger, and then there is also the tail binding domain. Those tend to be more an RNA-based to repair. So those were the mechanism. I'm going to highlight how it is used in the sickle cell disease, and the same method it is in thalassemia. So those are the four concepts that I explained previously. But this left box, it is basically adult-like hemoglobin AA. It uses the hemoglobin A T87Q. That's the Zenteglo and the Lyfgenia. So it's inserting a beta-globin or beta-globin-like. In the second one, it is the gene editing. What you are trying to do, it's increasing the fetal hemoglobin by targeting a transcriptor factor, the BCLA11A, or the LCA could be locus 2. It's a different mechanism that is not approved, but there was a study that was back in 2022 from Boston Children. Or you could target directly through the same CRISPR and Cas, either 9 or 12, the gamma globin, which is that Renicel study that I showed you at the end of my previous discussion. And finally, which is what that Beacon study and the ESCAPE study is aiming, which is the base detection. So that's the LCR and the BCLA gene. It is basically, I remind myself how I explained to the patient, it's a light. You turn it on and off in terms of that control. That will turn your turn your hemoglobin fetal production. I do want to make sure everyone is aware of this article just came last week from the adrenal leukodystrophy. This is about gene addition. This is another gene therapy and cellular therapy approved for adrenal leukodystrophy. This is a metabolic disease that leads to neurological degeneration, and really many patients have major disability and they die if they are not transplanted very early. So there has been gene therapy approved for this disease, but unfortunately, there has been 7 patients that they developed hematological malignancy, and that seems to be related. But I want to show that this is really different from, it's a different promoter that it is used than the promoter that it is used in the patient with sickle cell. It is the ABDR1. It is also induces higher level of expression, and it is adjacent to some of the myelodifferentiation. So that's really was higher risk of a disease, but because this disease is already associated with a high mortality, and because they're already going to get a bone marrow transplant, the FDA allowed this product to continue, and you will see so many of these patients will salvage with a bone marrow transplant when they develop. So the hematological malignancy developed in 7 out of the 67, so they still were able to salvage them with a bone marrow transplant, and the outcome was still around 92%. This is the gene editing mechanism that I showed you previously in the previous slide. And for the sake of time, I'm going to finish with this slide with some thought-provoking. I do think this is exciting time for gene therapy, but we are far from where we want to be. There is many challenges we have to address together, and now we started with the observation on the bedside. We took it to the bench. Now we have to go back and tell that what we are seeing in the bedside is not enough. First is the access. This is quite an expensive therapy. It's even in the most developed countries and the rich countries, given how much is the burden globally, we cannot deliver this therapy to the patient who are in need. We need to make it cheaper and make it more accessible with easier therapy to do. Second is the manufacture. This is quite long for patients who have been doing, we have done a lot. That mobilization is not easy for this patient. It's not walk in the park. We need to find better ways to make mobilization of these cells with either newer product from Plerixafor. And second, it is the company need to find a better way for the gene transfer and editing to be more efficient, have some more safety about the regulation, maybe have a suicide gene added to it, so if you develop any abnormal clone, you could turn it off. And also really from a conditioning therapy, exciting to have a newer study, but I am not certain that it is going to be in graft. We know, for example, sickle cell and also thalassemia have higher graft rejection. So we'll need to see how it will work out with the reduced intensity, but I do think it's important to work that out so we can address the concern about infertility and the risk for secondary malignancy in this patient. And our ultimate goal is one day we can do in vivo gene editing and no need for all of that chemotherapy and other complication. And with that, thank you so much again for the inviting committee.